divided into 4 parts. First, I will introduce what verification is. Next, I will explain how to write pattern and Testbench, including their syntax and usage. Finally, I will introduce you our entire simulation environment. First, let's introduce what verification is. So what is verification? Verification is used to verify whether the functionality of your circuit design is correct. It can also be used to make sure that you are implementing what you want, and that the net is converted from the spec match our expected results. The term testing and verification can often cause confusion. Testing is used to check whether the circuit is manufactured correctly. That is, after we complete the design and generate the netlist and send it to the foundry for chip fabrication, testing ensures that no error occurs during chip manufacturing. In summary, verification refers to checking the correctness of the circuit functionality. Testing refers to checking the correctness of circuit manufacturing. So what it actually is verification? Simply put, verification is a process of bug hunting. If we tape out a chip to the foundry for verification and later discover that the functionality is incorrect, the designer will no longer be able to modify it. Therefore, we must find all possible bugs before tape out and verify whether the design functionality is correct. Verification including the following aspects, and the most important one is of course the functionality. If functionality is incorrect, the chip we design will become useless. Once functionality is verified, we then consider aspects such as performance, power, security, and safety. Here are many verification methods. In today's step 3, we will use a simulation-based approach to verify that our design works correctly. In Lab 10, we will teach you how to use system log assertions and functional coverage for verification. In bonus lab, we will introduce Cadence tool to explain formal verification. In short, simulation-based verification means preparing many tests to test whether our design produces a correct result. Formal verification use a mathematical induction-like proof approach to verify whether your design results are correct. In Lab 7, we will introduce static timing analysis. If you want to verify whether your circuit timing meets timing constraints, you can use static and dynamic timing checks for verification. In Lab 8, we will introduce power-aware simulation, which will consider power as one of the performance evaluation criteria. Finally, you can also use an emulator or FPGA as a prototype of your design to verify whether your circuit functions correctly. Verification can generally be divided into 3 stages: preliminary verification, broad spectrum verification, and corner case verification. As a beginning, we perform a preliminary verification to test some basic specs, such as ensure that your design resets to 0 after a reset. After that, we proceed to broadcast a spectrum verification, where we feed test patterns into our design for verification. For example, we use generate random signal to verify the common cases that frequently occur. The final stage is corner case verification. Since randomly generated test data cannot cover some extreme cases, we need to design special test patterns to verify this corner case. Next, let's talk about the step in verification. First, generate stimulus, which are test signals that drive the design. Next, apply this test signal to a DUT, design under test for computation. Then compare the results from the design with the correct results. These steps are repeated continuously until all verification tasks are complete. After that, we measure the quality, cycle, and area of the design. If any error occurs in this step, or if the design does not match the spec, it indicates that there is an issue with your design, and you need to find a way to fix it. Let's talk about the two kinds of strategy for verification: directed testing and random testing. First, directed testing is for checking what we know, where we write out a specific test cases for verification. Since randomly generated test data may not cover specific corner cases, we need directed testing to handle those cases. On the other hand, a random test is for checking what we don't know and where we generate a large amount of test data. It covers a wider range but may also repeated test some data. In summary, directed testing is used to test specific corner, and random testing is used to test a broad range of scenario. This graph shows the relationship between time and coverage for random test and direct test. Coverage refers to the percentage of different cases covered by your test data. The higher the coverage, the higher the confidence that your test data can verify whether the design is correct. From this graph, we can see the random test can achieve higher coverage in a short time in the early age, because random test generates signal randomly, which allows it to quickly provide a large number of test signals for circuit verification. However, in the end, it may not reach 100% coverage. In other words, random tests can cover a vast and broad range of tests in a short time, but it usually fails to cover all corner cases. In contrast, direct tests require manually designing various tested cases. So in the early stage, its coverage increases more slowly than random tests. However, since you manually design the test cases, you can cover corner cases that random tests fail to reach, and eventually achieve close to 100% coverage. Yes, it takes significantly more time to reach a coverage level similar to random tests. So, should we use random test or direct test? Here is a graph showing the relationship between time and coverage. Coverage refers to the ratio between tested cases and all possible verification scenarios. We aim for higher coverage as it indicates that the circuit have undergone more robust verification. First, we need to build the verification environments. Next, in the early stage, it is recommended to use the red test for preliminary verification, which means directly checking whether the design resets to 0 after a reset. Covering basic specifications, then use random tests for the broad spectrum verification. Generating a large number of random test patterns to improve coverage. After that, we can limit the range of random tests to verify a specific corner case. Finally, to achieve nearly 100% coverage, some corner cases are difficult to cover using random tests, such as verifying overflow, which occur less frequently. Therefore, we should combine both methods for best results. Next, let's introduce our various design verification environments, which mainly consist of three files: Testbench, design, and pattern. In a 00 Testbench folder, you will find Testbench and the pattern. In a 01 RTL folder, you will find design. The relationship between these three files is shown in the diagram. That design is a circuit you need to design and test, also known as the design under test (DUT). And the pattern is responsible for generating test signal and handling the verification process. Pattern generates test input signal and send them to design for computation, and design computes the results and send them back to pattern. And testbed acts as a bridge between test design and pattern, where pattern's output is connected to design's input, and the design's output is connected to pattern's input. Finally, we mainly run the testbench .b file to generate waveform diagrams. By analyzing these waveforms, we can observe how signals change and use them to debug. Next, we will introduce how to write the content of the pattern. Here's a simple example. Following the order, pattern can be divided into 4 parts: part declaration, data type declaration, generate stimulus, and check result. First, part declaration and data type declaration involves defining the ports and specifying a data type for various variables. Next, generate stimulus refers to generating a test signal for the design to compute. Finally, check result is verifying whether the output computed by the design is correct. Next, we will introduce some elements used in the pattern. First, let's talk about the procedural block. This procedural block contains a simple pattern flow, which covers most of the tasks that need to be done in the pattern. A procedural block refers to the structure such as always blocks and initial blocks. We write the execution flow of the pattern inside a procedural part. It is usually controlled using statements like for, while, repeat, if, and case. Procedural blocks are divided into 2 types. One is the initial block, and the other is always block. The initial block cannot be synthesized, so it is mainly used in simulation files, such as in Python. It will only be executed once at the beginning of the simulation, and is used to simulate the initial stage of the circuit. The OS block is commonly used in design, and it can be synthesized. It will be executed if the condition is met, running the content inside the OS block. Here is an example of using an initial block. Suppose we need to verify a design, and we use a procedural block to test the max circuits showing in the top right. If we want to generate the waveform shown as the bottom right as the test signal in our pattern, you can write the code on the left like this. First, declare your test module as well as the input-output port. Next, use an initial block to simulate the change of A, B, and the select signal. At the beginning, all signal A, B, and select are 0. So we write A equals 0 and the select equals 0. After a delay of 10 time units, A and B and select signal change. So we write wait 10 time units, and A equal to 0, B equal to 1, and select equal to 1. After another 10 time units, A and B change, but select remain the same. So we write here. After another 10 time units, A and B stay the same, but select signal change to 0. So we write wait 10 time units, select equals to 0. Finally, when your simulation ends, remember to add the finish command. Otherwise, your pattern may not be able to stop the simulation. Next, let's talk about how to use text and function. If there is a segment of code that needs to be executed multiple times, writing it directly in line will make the code very long and difficult to read. In such cases, we can use text or function to write this code. Although text and function both serve the purpose of code reuse, they have some key differences. Text is more like a generic subroutine in the software. It is typically used to perform debugging operation or to behaviorally describe hardware. A text can have multiple input and output, allowing it to perform multiple actions. And function is more like a small circuit or submodule. It is typically used to perform a computation or to represent a combinational logics. However, it can only return a single value, making it suitable for simple computation or logical decision. In summary, text is useful for debugging and behavior description, while function is better suited for performing a mathematical or logical operation. Next, we will go into detail about how to write a text. If you want to declare a text, its format is shown in the diagram. After text, adding an identifier to represents the name of the text. And don't forget to add a semicolon. Declare the following parameter in output port and register. Then start writing the content inside begin end. Finally, add an end takes to complete the test definition. We will cover some example. First, example is the reset text. This is used to verify whether the circuit resets correctly. First, force clock to 0 before applying the reset signal, which prevents interference between the reset signal and the clock signal. Next, after waiting for a period of time, check whether the output signal have all reset to 0. Be careful, we use case inequality for comparison, which is exclamation marks equal, or you can use case equal such as 3 equal or triple equal. This ensure less unknown and high impedance states are considered. Before next example of text, let's talk about how to write the reset and clock. Taking a synchronous reset as an example, a synchronous reset means that regardless of whether it is at the card edge, as long as the flowing edge of the reset occurred, all registers will be reset. So the implementation can be written as a flower. First, we declare the clock period as a real type and define its value. For example, here the clock period is set to 2.5. Next, we initialize the clock to 0. Then we use always block to toggle the clock value, which generates a periodic oscillation which with a 50% duty cycle. At the beginning of the initial block, we force the clock signal to 0 until the reset flowing edge is applied. After that, we release clock and let it start operating. Since we are using a synchronous reset, we should avoid interference between reset and clock as much as possible. Thus, before applying the reset falling edge signal, it is better to prevent clock edge from appearing. That's why we use false clock equal 0. Next example is the input data text. Here we encapsulate the generated stimulus processed into a text for implementation. Typically, input data is provided to the design as the negative edge. Previously, we mentioned that the input signal are given as the negative edge. This is because the previous stage circuit has a delay, which is referred to as input delay, where this delay is calculated related to the clock edge. However, there are actually two methods to define input delay. Assign input delay as by absolute delay value. This method directly specifies a fixed time unit for input delay. For example, the input changes 1 time unit after past edge clock. If the input delay from the previous circuit is unknown, it is known. We typically use absolute time delay. Assign input delay as relative delay value, which is relative to clock period. This method defines input delay based on a fraction of the clock period. For example, the input change as the negative clock edge means the delay time is half of the clock period, which is why it's called relative delay value. This method is used when the exact input delay from the previous circuit is unknown. And why does ICEP prefer the relative delay value method? ICEP prefer the second method because the exact input delay of the previous circuit is usually unknown. If the input delay is known, we can adjust the delay accordingly. In contrast, we use absolute delay value as a drawback. If you modify the clock period but forget to update the input delay, it may cause a timing violation leading to incorrect test results. Thus, in most cases, using a relative delay value is more flexible and stable. Next example is the check output text. Here we implement two texts for waiting out value and checking output answer, respectively. As you can see, both outputs are also treated as the negative edge. Finally, don't forget to use case equality and equality for comparison. Now we will go through detail about a text. Here is an example of using a text. Looking at the convert text on the left side, we first declare the input-output ports, then we write the content inside a begin end. When you want to use this text, you directly call the text identifier, which here is convert, and you pass the input and output port into the text. On the right side, there is a similar example of declaring a text. However, this example does not declare any input or output ports. Hence, when calling this text, you do not need to pass any ports. You just call the identifier directly. The difference between the left and the right example is the convert text on the left has an input-output port, which treats the global variable temp in as an input variable and passes it as the initial value for local variable temp in for computation. The convert text on the right does not have any parameters. Therefore, the temp in inside the text is usually the global variable temp in. Pay attention that if some global variable named outside the text match a local variable name inside the text will use the local variable, and the local variable does not change the global variable's value. The behaviors are sent as Python or C. In short, be mindful about whether variables inside the text are local or global. We have just covered how to write a text. Now let's talk about how to write a function. When declaring a function, its format is shown below. After function, in addition to specifying the identifier, which represents the function name, you also need to add a type or a range before it. This specifies the return type or value range of the function. Next, you need to declare the parameter, input port, and register. Then you can write the content inside begin end. Finally, similar to text, you need to add end function to complete the function declaration. One important thing to note here is that a function inherently returns a value. so there is no need to declare an output port separately. Here is an example of using a function. First, we declare the function's content. Before the identifier, we need to specify the type and our range. In this example, the function add returns a 8-bit value. Next, we declare the parameter, input port, and register. For this instance, this example declare input 8 bits A and input 8 bits B. Then we can write the content inside begin end. One important thing to note is that inside the function, there must be a variable with the same name as the function identifier. Otherwise, there will be no variable to represent the function return value. For example, the function identifier is add. So inside the begin end block, we must have a variable also named add. When using the function, it works like this. Sum equal to A and B. We need a variable to store the function's return value, which also means that function must be replaced on the right-hand side of the equation sign. Here we summarize the difference between text and function. First, text can have timing control such as delay, act, and wait. Text can execute in non-zero simulation time. Since text may include timing control, text can have both argument or none, or for input and output can be declared optional, and the text does not return a value, and it can call by a text or a function, but it cannot be synthesized, so it cannot be used inside a design. Next, function cannot have any timing control. All operation inside a function execute with a simulation time of 0, meaning they complete instantly. And the function must have at least one input port, but cannot have only one output port. But cannot have a output port. And a function can be called by its name and return a single value. And it can be called by another function, but it cannot call a text. And it can be synthesized. Here we explain in more detail how to generate stimulus inside a text. Here is an example of generate stimulus. We randomly generate a large amount of text data for bulk spatial verification. Also, we read input data from a file to create specific input combinations for corner case verification. Generate stimulus methods are mainly divided into two types. The first type is to directly generate testing data inside the pattern using Verilog. The other type is to use other high-level languages such as MATLAB, Python, C, or C++. To write test signal into files and then read them into the pattern. This involves file I/O, which will be explained later. Now, how do we write Verilog random number generation? How do we generate it? We can use the following three system functions. First one is random. It returns a 33 bits sided number. The seed parameter is optional. If not provided, it will use its default seed value. Since random tables are the same on different computers, using the same seed will generate the same random values. So if you want to generate a fixed test signal, you can use the same seed. Second one is urandom. It returns a 32-bit unsigned number. The seed parameter is also optional. The third one is urandom range. It generates an unsigned number within your specific range. The maximum and the minimum range value should be passed into the function. Next, here are some example code for generating random signal in Verilog. For example, we can declare variables directly as integer or as fixed bit registers. And we can also choose to use the urandom or random function. This different choice will result in slightly different testing signal outputs. Suppose our goal is to generate a random signal in a range of 0 to 6. Which of these methods will correctly produce values within that range? First, the very important conclusion. No matter whether the left operand is declared as signed or unsigned, if either of the two operand is an unsigned variable, the operation will be treated as an unsigned operation. First, let's compare 1 and 2. The difference is that the button expression in 1 use the random function, while 2 use the urandom function. These two functions return signed and unsigned variables respectively. Since both operands on the right side of the equation are signed, this operation becomes a signed operation. However, because number is also a signed variable, the value returned to a number might be negative, which falls outside the desired range of 0 to 6. The right one, if we use the method on the left, on the right, since one of the operand on the right side of the equation is unsigned, this will be an unsigned operation. The value returned to the number will be within the range of 0 to 6. Making 2 is a correct approach. Next, let's compare about the 3 and the 4. Their difference also lies in the operand types, which number being declared as unsigned in both cases. In this expression, there is one unsigned variable on the right side of the equation. So the operation is treated as unsigned. This ensures that the value returned to the number will be within the range of 0 to 6. However, in this case, there is no unsigned variable on the right. So it is treated as a signed operation. Since number is declared as unsigned, the value returned might fall outside the 0 to 6 range, possibly it become negative. For example, if the right hand side evaluates to -3, it will be stored in a number as 4 bits 1101. From an unsigned perspective, 4B1101 does not represent -3. but instead equals to 13, exceeding the desired range. In short, if the right-hand side of the equation performs sided operations, it produces a sided result. Assigning that sided result to an unsigned variable on the left side might lead to out-of-range value. Therefore, when generating random signal in the range of 0 to 6, the key is to use the correct operation type, preferable an unsigned operation to avoid error. Originally, we might declare directly write 7 as a constant, and it is by default a 32-bit sided integer. However, if we want an unsigned constant, there is another way to write it. In this example, we use the notation single quotation mark D7, making this constant an unsigned variable. This ensures that the entire operation is also an unsigned operation, thus produce the correct range. The second method to generate stimulus is through file I/O. File I/O refers to file import and export. Sometimes we need to import information from other files, such as TXT files, into our pattern or export some record to a log file. First is calling a file, which means opening a file. We can use the fopen function. Depending on the parameter we provide, it will return different type of descriptors. You can think of the descriptor as a 32-bit integer, where the value acts like a serial number, and we can use the serial number to access different file permissions. A descriptor are divided into two types, file descriptor and multi-channel descriptor. The difference lies in whether the type parameter is included when calling the fopen function. First type, if our fopen function includes the type parameter, it returns a file description. The type parameter specifies how the file is used, and there are various options. For example, if the file is for reading, the type is set to R. If the file is for writing, the type is set to W. The most significant bit of the descriptor is always 1, while the remaining bits represent different opened file. The second type, if our fopen function does not include the type parameter, it returns a multi-channel descriptor, which also allows writing but not reading. The MSB of the multi-channel descriptor is always 0, while the remaining bits use a 1-hot representation, where each bit represents an output channel, and meaning that you can open up to 31 file channels simultaneously. This method allows writing to multiple files at the same time. We can over two different multi-channel descriptor to create a descriptor that operates on 2 files simultaneously. For example, by ordering file 1 and file 2 from this example, we get 0110, which means writing to both test.txt and test2.txt simultaneously. And it is important to note that After using a descriptor, you must remember to close the channel. This ensures that the channel can be used again later for reading or writing new files. We use the fclose function to close the channel. When we open a file, we need to use functions to read or write data to the file. First, we will explain how to read data. A read function are similar to those in C, including fget C and fget S, and fscanf and random map. fgetC reads 1 byte at a time from the channel opened by the descriptor and the store is in the variable C. And fgetS read a string into variable I until the string is filled or a new line character is encountered. And fscanf reads data from a file based on the specific format and store it into signal variables. The example below read data from a file opened by the descriptor file input. In this file, the data is presented in the format OPA equal to 101. And we want to store the value of OPA and OPB into the variable OPA and OPB declared in the pattern file. Therefore, we write OPA equal to %D and OPB equal to %D in the test section, and place OPA and OPB in the signal list. The %D format specifier means the data will be read as decimal values. So OPA and OPB represent 101 and 101 and 1010 respectively.
这个 decimal 是3个字了才对。
但是它这个就会读出来就是101啊。
哦，对。
Okay. If we want to read the data in a different numerical base, we can replace %D with %B for binary and %H for hexadecimal. If the data is successfully read, the variable RC will be set to 1. Among these 3 reading methods, fscanf is the most commonly used function, and 4 is readmap. This function requires specific input file format and specific reading method. They are mainly used to read data from a file and store it into an array. And readmap requires that each number in the file be the binary format, and the other one is hexadecimal format. For example, using readmap, the file requires a specific format. Before the data content, you need to specify its address, which indicates that the following data should be stored starting from this address. In other words, it specifies from which level of the array to begin storing the data. Only after specifying its address can the data content be written. For example, the following 2 cases. Here is 2 simple examples for readmap. The left one, mem is declared as an FB array with address ranging from 0 to 7. And as 002 means that the following data begin stored from the second level of the array. So those data will be passed in the second, third, and fourth and fifth levels respectively. And as 006 means the following data starts from the 6th level of the array. So those data will be stored in the 6th and the 7th levels respectively. If certain levels are not specified in the file, the data will be unknown. Which in the right example, mem is declared as a 16-bit array with address ranging from 0 to 7. Just like the left example, data have been written to array 2nd, 3rd, and 6th levels. The underscore does not affect our interpretation of the data. These two commands are commonly used in memory rewrite operations because memory storage follows a structure similar to this array format. Here are two special cases that students might have thought about. In both of these cases, mem is declared as an 8-bit array with address ranging from 0 to 7. The left example demonstrates that if new data placement overlaps with previous stored data, the new data will overwrite the old data. The right example shows that if data is placed outside the valid range of the memory array, it will not be stored. Next, let's talk about how to write data to an external file. There are 4 commonly used commands: fdisplay, fwrite, fstore, and fnometer. This command takes the same parameter, which consists of a descriptor, a function, format, a specifier, and argument list. Descriptor specifies the file you want to write to. Format specifier defines the format of the text you want to store. Argument list further specifies which variable values should be stored. Looking at the example in the slide, we will store OPA plus OPB equals to sum in a decimal format into file output. And the difference between these commands lies in whether they add a new line and in their execution order during simulation. New line handling is simple. fdisplay and fstore add a new line, while fwrite and fnometer do not. The execution order of active event and nometer events will be introduced in the later slide. Now, just remember that fdisplay and fwrite execute at the same time, whereas fstore and fnometer execute at another timing. All 4 commands can output data to a file, but the main difference are whether they add a new line and the execution order in simulation. This slide provides some more functions for writing data into external files. These are essentially variations of the 4 functions we introduced earlier. The difference lies in the data format used for output. By appending H, B, or O to the original 4 command, we can specify the numeric base for output. If no suffix is provided, the default format is decimal. One important note, if the format specified in the function is defines a numeric base, this format will take precedence over the suffix. Now we have learned how to open, read, write, and close files. Let's look at a practical example to reference this concept. First, opening the file. Here, in read and out file are declared as integer to store the descriptor returned by fopen. The type specified after fopen depends on the purpose of the file. Next, reading the file. The fscanf command is used to read data. The parameters passed to fscanf include file descriptor with format and variable to store the retrieved values. Then, write to the file. The fdisplay command is used to write data. The parameter passed to fdisplay include file descriptor and a write format, a variable containing the data to be written. Finally, we close the file. The file in read and the out file are closed using fclose. Finally, introduce display information, which refers to displaying information about the pattern computation process on the terminal. The main display commands include display, write, stroke, and nometer. These commands are essentially similar to the file output commands discussed earlier. The only difference in this display command does not have the prefix f and does not require a descriptor parameter. You can refer to the file output section for more detail. As previously mentioned, both file IO and the display command require setting the format for input or output data. This slide provides a reference list of commonly used formats. And here are some references. Next, let's explain the difference in execution timing. First, we need to understand the order of the simulation. In the world of software, programs are typically executed line by line in order, meaning that only one thing happens at a given time. However, in the world of hardware, circuits can perform parallel computation without being restricted by the order of the program lines. This means that multiple operations can occur simultaneously at the same moment. This leads to a problem. How can we use software which process instructions sequentially to simulate hardware circuits that compute in parallel? To handle this, we need a special mechanism to manage such situation. We introduce a virtual timeline and divide it into 5 event queue, each with a different priority level of execution. First one is active event. The first to execute this includes blocks assignments such as assignment in the combinational circuit, pre-computed right-hand side of non-barking assignment, and the sequential operation, and continuous assignment additionally. Okay, 重讲. These include blocking assignment, such as assignments in combinational circuits, and a pre-computed right-hand side value of non-blocking assignments, and sequential operations, and continuous assignments. Additionally, display and write are executed in this queue. Next, inactive events are executed if a blocking assignment is proceeded by wait 0. It falls into this category. Since this is a zero delay operation, it technically occurs at the same time, but executes slightly later than standard blocking assignment. And the third one is a non-blocking event. This simulation software assigns the pre-computed right-hand side value from the active event to the right-hand side variable. And the fourth queue executes the nominator event, including commands like nominator and store. One key takeaway here is that due to execution timing, write and display cannot be used to observe the result of non-blocking assignment, as the assignment occurs after write and display executes. Instead, you must use store and nominator to properly observe those results. Finally, Verilog PLI events executes only after all four of the above have been processed. This includes commands like fsdb downfile and fsdb downbars. Within the send event queue, execution order follows the sequence of code lines. Here is an simple example. Let's look directly at the initial block. At the start, after opening the file a equals to 0, b equals 0, then after a delay, line 11 and 12 and 20 describe what happened at the time unit 1. Let's analyze what happened at this specific timing. First, we execute active events, which including blocking assignment, continuous assignment, the right-hand side of non-blocking assignment, and the display and F writes. So the first step is executing A equals to 0 and B equals to 1, and evaluating the right-hand side of the non-blocking assignment, and executing fdisplay and fwrite. As a result, in the first line in the terminal output will show display A equal to 0 and B equal to 1. Then fwrite execute. But since it's writes to a file, there is no visible output in the terminal. After active events finish, we execute inactive events, which are zero delay events. This include the zero delay and the zero delay display. So the terminal output will now show this. Now we assign the compute right-hand value of the non-blocking assignment to the left-hand variables. The right-hand side value of B, which is 1, is assigned to A, and the right-hand side value of A, which is 0, is assigned to B. Now, A become to 1 and B become to 0. And next, we execute nominator events, which include nominator and store. As a result, the terminal output now shows nominator and store. Finally, we execute Verilog PLI events, which include commands like fsdb downvar and fsdb downfile. This ensures that all executed events are stored in the fsdb waveform file for later debugging. Next, we will talk about how to write the content of the testbench. It was mentioned earlier that the testbench is a file that connects the design and the pattern, acts as the bridge between the design and the pattern. So when running verification, you only need to run the testbench.b file. The content of the testbench mainly consists of 3 parts. The first part is defining the timescale, which represents the simulation time unit. The second part is the method for dumping waveform files. The third part is connecting the ports of the design and the pattern together. First is the method for defining the timescale. The timescale consists of 2 parts, time units and time precision. Time unit represents the basic unit of time. The delay and the clock period written in the pattern are also calculated based on this unit. Time precision represents the minimal precision of time, indicates the smallest time interval that can be represented. And time precision should be small enough to accurately represent all the required time values, and is usually 10 to 100 times smaller than the time unit. Here is a simple example. If we want to set the time unit to 1 nanosecond, and the precision is 100 picosecond, it should be written like this. This example also highlights a common mistake. As we mentioned earlier, the time precision must be accurate enough to represent the required time units correctly. Looking at the expression on the right side, we see the cycle divided by 2 equal to 1.25 nanosecond. To accurately represent 1.25 nanosecond, we need a precision of at least 10 picosecond. However, in this case, the precision is only set to 100 picosecond. As a result, the 1.25 nanosecond value will be rounded to 1.3 nanosecond, which deviates from our expected simulation behavior. So what should we do? At this point, you can adjust the timing precision to 10 picosecond to avoid rounding errors. Or you can set cycle to 2.4 instead of 2.5, which can also prevent rounding errors. Below are several examples where the last 3 examples show rounding due to insufficient precision, which may lead to unexpected timing issue. In conclusion, when writing the timescale, you must be careful. If not written properly, it may result in insufficient precision and causing rounding errors. Next is the dumping waveform section. Dumping waveform refers to generating waveform diagrams. Different software tools require different file formats. So when dumping waveforms, we generate the corresponding waveform file based on the software being used. If you are using Verilog HDL IEEE, a standard set the dump waveform file extension to VCD. If you are using ModelSync, set the file extension to WLF. And if you are using Cadence NC Verilog or Simvision, set the file extension to SHM. If you are using Synopsys VCS, set the file extension to BPD. Lastly, in iStack, we primarily using Synopsys Verdi, which read waveform files with the extension FSDB. There are some commands we use in the testbench when generating waveforms. FSDB dump file. This command generates a waveform file while FSDB name is the name of the waveform file. Since waveform files are usually large, you can add a limit size parameter to restrict the file size and avoid running out of storage. One important thing to note is that when running a Lec03 get-level simulation, if you no longer need waveform debugging and don't want to generate an excessively large waveform file that might exceed the service quota, you can comment out the FDV dump file line in the testbench to avoid a storage issue. And the FSDB dump bar, this command specifies which signal waveform should be included in the waveform file. The instance parameter specify which modules waveform to include. The depth parameter defines how deep within the instance the signal should be included. The option parameter allows for additional setting when generating the waveform file, which will be explained later. And the SDF annotate. SDF stands for standard delay format, which means that when generating waveform files during simulation, an SDF file is included in the simulation. The SDF file record the timing information after circuit synthesis. So when performing a gate-level simulation, we must include the SDF annotate command to accurately simulate the circuit. And let's introduce the parameter inside FSDB dump bar. The depth parameter specifies which layer of the signal to dump. 0 is dump all module signal. 1 is dumps only the current layer signal. When instant is set to the testbed, it refers to signal inside testbed. 2 is represent to dump the current layer and the next layer signals. That is, this module and the first level submodule signal coded inside this file. The larger the number, the more layer of signal will be dumped. Usually, we set the depth to 0, meaning all signal will be dumped. Option parameter. There are multiple choices for option parameter. The first one, IO only, will display IO port signal. Register only will display register type signal. And O includes memory and multiple dimension array and packed array structure and union packed structure signal. Among them, MDA is the one we use more frequently. By default, Verilog does not dump multi-dimension arrays in the waveform dumps. You need to add MDA dimensional array to dump multi-dimension arrays and the memory signal. And this is the flowchart for dumping waveforms. In RTL simulation, when dumping waveforms, we only use the design file, and the generated FSDB file is usually named design FSDB. And in gate-level simulation, after synthesis, we will generate 2 files. One is design syn.b, which is a netlist of the synthesis circuits, and design syn SDF, which contains the timing information after synthesis. When debugging waveforms, we must use the information from these two files to generate the FSDB file. And the generated FSDB file is usually named design S1 FSDB. And this is the syntax for dumping waveform. Since we use different files to verify simulation in RTL and GetLabel, the dump waveform syntax is also different. We use if-else statements to differentiate between the two types of simulation. First, in RTL simulation, we dump a file called design FSDB, then use FSDB dump bar to set it to dump all signal, and the signal inside multi-dimension array. Next, in gettable simulation, as mentioned earlier, we need to include timing information to check for timing violations, which means we need to use the SDF file. Therefore, we must add the SDF annotate command. So the simulator will consider the timing information inside the SDF file. Thus, in gettable simulation, SDF annotates is required. The first parameter is the net of the SDF file. The second parameter in the gettable is the gettable module named that the SDF file corresponds to. This link the timing information to specific module. For example, here we link the timing information to the DUT module. Make sure double check that the module name is correct. Finally, we have the post connection section, which is connecting the ports between the design and the pattern. First, we declare the pattern module and the design module. Since we only need to connect the input and the output of the pattern and the design, we can only use wire signal for the connection. And finally is the environment section. In the IC lab course, we usually divide a lab into multiple files represent different flows. And the reference files for this flow are placed in their respective directories. This directory mainly serves to help you better understand the entire design flow. Testbench is the directory content file related to pattern and testbed. The RTL contains the file related to RTL simulation. And the SYN directory contains file related to synthesis. And gettable and get folder related to a gettable simulation. And this folder contains file related to memory. And in Lab 5, you will learn to use SRAM. And the APR, this directory contains file related to APR and auto place and routes. You will use this in Lab 12. And post this directory contains files related to post simulation, and you will also use this in Lab 12. And you can check the contents in each other folder. Okay. Finally, you can use quota list command to check whether your server is out of quota. And remember to encrypt your pattern or design when you and your partner share your patent, and you can run the VCS plus auto protect patent DB, and you will generate a patent BP in the directory. And if you want to save the module name and port declaration, please use auto to protect. Okay. And
okay, now this is the end of this lecture. So let us take a break for 10 minutes, and we will introduce this the Lec03 assignments later. Okay, take a break. Okay.
for translate harvester request.
Sorry, I forget to turn on the microphone. So
Oh.
I let TA restart this assignment. Okay, sorry.
Okay.
Okay.
Welcome to this web tutorial. Okay. In the area of the big data, data is often stored as a complex hierarchical tree structure scattered across vast memory space. And in this lab, we have two core operations, harvester and sort. The harvester is a prefix efficiency and represented as a whole arithmetic equation, which I will introduce in the later chapter. And in this step, we will also use DRAM as our data source and storage memory. To reduce memory access latency, you may need to perform interleaving to meet this lab specification. Next, let's look at the entire system, which mainly consists of 4 modules. Pattern is the module responsible for generating test command and verify results. Your preliminary test in this step is to complete and refine the pattern. And next, harvester. This is the core module you will design as the master of XI4 lights. It is responsible for issuing a memory assay request and perform arithmetic operation and sorting logic. DRAM control is another interface module you will need to design. And as a slave of AXI4 lights, it is responsible for translate harvester requests into physical DRAM instruction. Next one is pseudo DRAM. Pseudo DRAM is a simulation model provided by the TA and used to store the tree structure and data. And its timing specification will be strictly very fast. Note that when harvester communicates with DRAM control, we use AXI4 lights as the transmission protocol, and the DRAM control then access data in pseudo DRAM through the physical DRAM bus. And in this step, you need to complete the pattern. The TA will provide a test encryption designed to ensure that your pattern meets the specification. In addition, you will need to implement 2 RTL code, harvester and DRAM control, and verify them using the pseudo DRAM provided by the TA to complete this step. And first, we will introduce the data arrangement in DRAM. 太小，再大一点啊！可是我这样子。DRAM is divided into 4 banks, and each bank has 64 rows, and each row contains 56 columns, and each word is 64 bits in size. The address space is roughly divided into a system area, which is row 0 to 31, and storing the read-only tree structure, and the rewrite random data area is located at 33 to 62 row. And the next one is a general purpose buffer, which is located at row 63. And you can refer to a diagram to understand the data arrangement. Second, next we will introduce 2 basic operation and 2 full-stack operation that this step will perform. The first one is read. When a read command is received, the system needs to read the entire row of the data from the specific blank and row. Pattern will input you in blank and in source row. Since a row has 256 columns, you need to sequentially output the entire row of data for 256 consecutive cycles using all data and all weighting. When you performing a write operation, you will receive a write command, and you write a single in data entrant to the specific bank and row. After completion, simply write out value for one cycle. And the pattern will give you a whole row and totally 256 words in sequentially. And you should write it back to the destination row, which is range from 32 to 62 row. Next is calculate mode. In the DRAM system area, we have planted prefix expression tree. And your task is you need to process for tree sequentially or in parallel, and extract the final result. And the root node of the tree must be located in the column of 0 of the in-source row. And take an example for this. The red one is always the tree location, the tree's root node location. So if we give you the in-source row is 0, you must perform this tree and this tree and this tree and this tree. For bank tree, you need to traverse. And all operations are for 64 bits signed integer. Tree nodes are divided into 2 parts. First one is type 0, represents numbers, and type 1 represents the operation, including addition, subtraction, and multiplication, and the should write. And you don't need to worry about the invalid case. Here we'll review the overflow case in the pattern. Like the final false tree calculation results must be output strictly in the order of bank 1 and bank 0 to bank 3 for a consecutive cycle. The final one is sort. You need to collect data from a specific row in for bank, and 256 records per bank, and for a total of 1024 words. And you need to data must be compared based on the data field 62 to 32, where correspond to the least square. Now, if the data with the same value are encountered, the data with the smaller original address will be sorted first. And the 1024 sorted records must be written back sequentially to the 4 specified target row in the bank. After completion, our value will be raised for 1 cycle, and the pattern will check the DRAM variable. Now is the communication protocol. Many students have likely learned about AXI-related communication protocol in other courses. The TA will briefly reiterate them. HI4 Lite is a simplified version of AMBA HI4. Specifics is designed for low throughput, control-oriented register access. And compared to AXI4, the core feature of AXI for light are AXI for light has no burst. It means that only one data engine is transferred at a time. And you need to use ready and ready to handshakes and allowing a master slave to mutually throttle back pressure. And the A-type for lights retain the 5-channel architecture of AXI. First one is address, right address channel and right data channel and the right response channel. Then is read address channel and read data channel. Each channel follows the same handshake rule. And when the master sends data and daily, very poor high. And when the slave is willing to receive and provide data ready for high. And at this cycle, we handshake successfully. This step uses AXI and adherent to the following specification. Briefly introduce this web form. When we want to write a data in a specific location, the master will provide the A value, which means the AW address. This data is valid for the slave to receive. And when slave is ready to receive, we will provide the AW ready this signal, and we handshake the slave, and the slave receive the address of the right data. And then master will transmit we want to write the data to the location, and we will provide the value and give the right data, and the slave will provide the ready, and we handshake again. And when slave is write completely, it will provide the B value, which means its write already success, and master will give the ready, and we handshake again. And the following is some specification for this lab. The part highlighted in the red require corresponding verification logic in the pattern, and the violation will result in an error in the pattern. First one is the dependency. For this lab simplification, in a write operation, the address channel AW value must go high earlier than or equal to the data channel W value. And the master must never send W data without the corresponding AW address. And there's other spec. The first is timeout spec. Handshake signal cannot wait indefinitely. For example, after AW value goes high, ready must go high within 50 cycles. And after read-write data process is complete, the response channel must be provided within 150 cycles. This is 150. And loss violation, any of these will result in an error from pattern. And the other is the stability check, which means when your step is not ready for receive your request, then your value and address cannot change, but should remain stable until value goes high. And read channel is the same. And read channel must obey this in order response, which means because read operation supports outstanding, but the order in which the slave return read data must be exact the same as the order in which the master send AR address request. For example, if the master send address A, then address B, the slave must respond with address A, data A, then data B. The next one protocol is the physical DRAM interface. And after DRAM control receive an AXI request, it need to transfer it into physical DRAM instruction, such as activate and read, write, or charge. The pseudo DRAM provided by the TA will simulate the physical latency of real DRAM and must be strictly adhered to. And first, we will introduce the four commands. The first is activate. Activate this command is responsible for opening a row in a specific bank. And rewrite responsible for reading or writing data. And the pre-charge responsible for closing an already opened row. And now we are likely to check the timing constraint. A real DRAM is filled with capacitor and physical circuit, so operation require waiting. Pseudo DRAM replicates this physical delay. Your state machine must strictly adhere to the following four core timing parameter. Otherwise, data correction or instruction will be ignored. TRDC is the raw address to current address delay. This is after when sending an activate command to open a row, you must wait 2 cycles before sending a read command or write command. And TCL, which is response to cache latency. This means after sending a read command, the data will not appear immediately. You need to wait 3 cycles for the data to appear on the DRAM read data along with the DRAM ready signal. And for write, DRAM write data is sent simultaneously with the write command. Next one is raw pre-charge time. After we issuing a pre-charge command to close a row, you must wait another 3 cycles before issuing the next activate command to the same bank. And the next final one is the row active time. Once you open a row with activate, it must remain open for at least 5 cycles before issuing a pre-charge command to close it. Okay, now we will look back to look some example. This operation sequence. The first is the address masking. We combine for control signal, CS and RAS and text and WE in a we compile this in and send it to the DRAM command, and you can look out this lookout depot, implement this lookout depot. Okay. Okay. Here is a very important hardware detail: the address masking. The DRAM address pin is shared. When you issue and activate command, this line should hold the raw address. And when you issuing read or write command, this line should switch to the current address. And there is some example. For we want to read data from pseudo DRAM, your controller must follow this sequence. First, you must send activate command with specify bank and raw address to activate the bank of the row of the bank. And then you need to wait to cycle for DRAM to open the row. And then you can send the read command with the you want to read the bank and the current address in the row. And you will receive the data after 3 cycle delay. And if you want to access the different row in the same bank, you must first send the pre-charge command, which will close the row, and then you can send the activate command again. And the pre-charge command should wait for 5 cycle after activate command. The write cycle is similar to read. And a reminder, bank interleaving. Because of the waiting time for the TRCD and the TCL, the data burst can be idle. The specification allows operation from the different bank to overlap. That is when bank 0 is waiting for TRCD or TCL. Your controller should promptly issue an activate command to bank 1. This is the key to improving your throughput and saving the performance. And now we returning to the harvester controller. System is okay. First, we will send the involved value to design the mode. And the mode is represented to as follow. And then the following 1 cycle, we will send you the value, and you will receive a bank or a source row or distant row or data according to the mode operation. And your system complete all when your system complete all the calculation and writes are very high, and the output length of the out data must be determined based on the in mode, and this is the cycle time you must to output. Oh, okay. Finally, let's look at the hardware limitation and the scoring mechanism. Let's determine success or failure. The first one is the this step is using the asynchronous reset, and all your outputs must be reset when when active low reset edge. Okay. And all your design harvester DRAM control and the DRAM are synchronous at the positive edge of the card and operates at the same clock rate. And the execution latency of each operation of each pattern is limited in 10,000 cycles. And the area of the after synthesis is limited in 7,500,000 micrometer square. And the maximum clock period is set to 40 nanoseconds. And your synthesis lifetime is may not exceed 1 hour. And now is the grading policy. The first one is Testbench. In this time, you will complete the pattern by yourself. Your pattern need to be rigorously checked against 5 main spec and 6 AXI spec. If the design is flawed, your terminal must print the corresponding spec X is failed, and immediately terminates the simulation. Below is the description and the scoring for each spec. If more than one spec is violated, print them in this order. And please ensuring the following commands are printed on your terminal. After all specs are complete, you can use the 07 check pattern to verify your pattern. And the second demo regarding this pattern will be not scored. Next one is the design functionality. Here we'll use our prepared hidden version of the pattern and the pseudo DRAM to test your harvester and DRAM control, and to verify 100% functionality. And the second demo will receive 50% discount. And the performance formula is cycle time multiplied with total latency and the area squared. The faster your design runs and the smaller its area, the lower this value will be, and the higher your score will be. The second demo ranking is separate from the first demo ranking, and the score will be 50% discount. And if when submitting your file, please remember to upload pattern, harvester, and the DRAM control. When performing the synthesis, please add the design you want to compose after 01 run DC0. Which one you want to synthesis? You can specify harvester or DRAM control. And there is a reference waveform. Input waveform. We will first send you the mode value and the value mode, and next cycle we will give you the specific bank or source or the destination rule according to the mode selected. And next is AXI waveform. The first is the operation rate. The first we will send a valid for address and we handshake, and then we will read the data when Steph place the valid signal, and we handshake again and take the data. The final one is the physical DRAM interface waveform. And you can see this. We take read for example. And the first one we will send the activate to activate the bank 0 and the row 7. And then after 3 cycle latency, we will send the read command and send the current which current we want to read. And in this case, we send the bank 0 and the 77 column. And then we will receive 3 cycle delay after we send the read command, and we'll receive the data from the bank 0, row 7, and the column 77. And then if we want to read another row and another row in this bank, we must send the precharge command. In this case, we precharge the bank 0. Then after 3 cycle latency we activate again the bank 0 and the row B. Then we will send the read requirements as the send in the below above. Okay, and this is the right cycle for you to check. Okay, let's go. 我在用中文名字吗？
你要吗？
不是这样。
The DAS does he need to speak in Mandarin once? Okay.
Raise your hand.
Okay.
Got
it. So let's we'll continue.
好，那我再用中文讲次。那这是今天的 lab， 然后这个 lab 主要会有2个主要的操作。那第一个就是一个 harvester， 然后它里面就是一个prefix efficient tree， 那你需要去那个走过这个 tree， 然后它代表的就是一个适者运算的式子，然后你要算出它最终的结果。那 sort 的话，你就是把那一整个 row 的值全部 sort 排序好，然后再放回去我们的目的地，然后这样就可以了。那整个系统的架构就是说，我们会有这个 pattern， 然后跟 harvester， 然后跟一个 DRAM control， 然后跟一个 DRAM。那 pattern 就是用来传送我们的那个看我们是要做 read write 还是harvester 还是 sort 嘛？那然后它也会去 check 我们的 result。那另外的就是你们必须在这个 lab 中，你必须把这个 HI 的讯号再拉回我们的 pattern 去做HI spec 的检查。就是刚刚我们有讲到，我们有5个主要的spec， 然后跟6个HI 的 spec。好，那 harvester 它就是作为跟 pattern 还有 DRAM control 沟通的一个桥梁。那 harvester 它就是要去做刚刚说的那个适者运算，然后跟 sort， 然后它如果需要跟 DRAM 沟通的话，它需要先透过我们 HI 这个 for lights 的 protocol， 然后去跟 DRAM control 做沟通。然后之后 DRAM control 它会再用这个 physical 的 DRAM bus 去跟 DRAM 去做沟通，这样子。好，那这是DRAM 里面的资料结构。那这个 DRAM 它是被分成4个 bank， 然后有每一个 bank 它会有64个 row， 然后每个 row 会有256个 column。那这个 DRAM 的 address 的 area 它又被分为3大块。然后第一部分是这个 system 的 area， 它只能被读不能被写，就是它是存放我们的那个
prefix equation tree 的地方。那刚刚有提到就是 prefix equation tree 它会有一个 node 嘛，就是你需要从它的最根本的地方去 traverse 它整个 tree。那这个 node tree 的位置就是在红色框框这个地方，就是统一放在每个 row 的第一个 column。对，然后这个harvest 的这个 mode 呢，你就需要我们就会给你一个 row，然后这个 row 就是你必须要去比如说 row 0好了，那你就要去 bank 0的这个 column 0跟 bank 1的这个 column 0跟 bank 2的这个 column 0，这4个 tree 你都需要走完一遍，然后并计算出结果，然后所以你就会有4个值的输出在 output 上这样子。那下一个就是一个 random area， 它就是助教可能会要求你在这边做 sorting 之类的，它就是一个可读可写的 area。那第63个这个 row 呢，每一个 bank 第63个这个 row， 它是给你们拿来做运算或是储存的一个地方，就是希望你们不要开很大的 register array， 但你们可以透过去跟DRAM 沟通的这个 latency 来换取你们的 area 的降低，因为我们这是 performance 是 area 的平方。这样好，那 rewrite 这个 operation 应该没什么问题，就是主要就是read 的话，我们会给你一个source row， 那它就只能去我不会让你们读你们自己的那个 general purpose 的那个 row， 所以你们就是它就是 range from 0到62，然后你就需要 output 整个 row 的那个256个 column 的值，然后在256个 cycle，依序 output 出来。那 write 的话就是我会给你们要写到哪个 bank， 然后跟写到哪个 row， 然后我会给你256个 cycle， 然后你要帮我写到相对应的位置去，然后你之后你完成之后就是铺害一个 cycle 的 out value， 然后我的 pattern 就会去检查你的 DRAM 是不是跟我的 golden 一模一样，然后这个检查 DRAM 的 golden 它不会去检查那个第63个 row， 所以那个第63个 row 你们可以看你们自己的需求使用这样子。那接下来就是这个 tree 的部分，我刚好像没有走过一遍，那反正就是这个东西就是 root 那你就会从 root 开始拿，然后从左边开始拿嘛，这个 prefix 你可能要去看一下它是怎么走的，那它是从左边开始，那当我们的这个 node 左边的值跟右边的值都有之后，我们就开始做运算。那像我从加开始走，然后就走下来，然后看到左右都还没有那个都不是数字，那我们就会继续往左或往右走。那看到 A 是数字，那我们就回来，然后这里有没有画笔？好，我们就是这样走，然后这样走，对，这样子，然后再这样子，这样子。这样走回来，那你的运算就会像这个 equation 一样，就是 a 加上b shift c， 然后加上这个 d 乘上1减 f 这样子，然后你就要这样去走这个 tree。那好，然后刚好我们有讲到，就是这个 tree 它的最大的深度是80%，就是你最多会有255个leaf。就是最多会有255。OK， 助教等下会再更新这个 PDF， 因为这好像是还没有更新的。然后这个64 bits 的这个 Word 的format 就长这样子，就是如果是这个 type 是0的话，那它就是代表是数字；那如果是1的话，它是代表是那个操作值。那操作值它的就定义在这个 OP code 这个地方。然后如果像是我们假设我们要走左边的话，我们就要去看这个 left pointer 嘛。然后如果我们要走右边的话，我们就是看这个 right pointer 指到哪边。然后这个16 bits 就是指向这个 就是我们敌人的那个位置，2 bits 的 back， 然后跟6 bits row， 还有8 bits 的 color。好，然后这里是说就是数字，这个 tree 如果你有遇到数字的话，就代表它左边跟右边都不会再有任何节点。那左边跟右边这个节点，我会用0叉 FFFF 这个来表示它，这样子就表示它已经是最后一个了。或是你看到 type 是0的话，它就已经是最后一个了。好，然后所以你就要去这4个 bank 的那个 row 的 tree 你都要走过一遍。然后 source 的话就是会给你一个 row 的，然后你这个4个 bank 的那个 row 的所有的值都要拿出来 sort， 所以就是从256个 column， 然后4个 bank， 所以是 total 就是1024个 word。然后一样会给你一个 distance 的 row， 然后你需要把sorting 完的这个scan 的 order， 然后存到这个 distance 的 row 上面，然后一样 output 一个 cycle 之后，助教 pattern 就会开始 check 你的 DRAM。那 A 叉 I protocol 应该不用再讲一次，就反正就是 handshake 的一个过程。然后我等下会再放一个关于 HIF Lite 的讲义放在E3上。好，然后这个 lab 比较特别，就是你不需要等待你的不需要等待 respond 回来，你就可以继续送你的下一个 address 跟data。那你不能你不能在没有 address 的前提下就送 那个 write data。好，然后这些标红字的就是你需要在那个你的 pattern 里面做 check 的部分。对，
部分就不多讲了。
然后最后是这个 physical DRAM 的部分。好，好，那我从 in output 这边开始讲好了。就是如果我们要去存取这个 DRAM 的话，我们需要送给它一个 command 嘛。那这个 command 就是这4个东西的组合。那这4个东西，你就可以用这个lookout table 去把它做出来就可以了。然后就分别会有这些 active 或 rewrite 或是 pretry 的 command。那那根据不同的 command， 那你需要去送那个 address 嘛？那这个 address 刚刚有提到，就是它是一个共用的一个 max， 就是当你是送 ATBase， 你要打开一个 raw 的时候，你就要送 raw 的 address。当你是要读或是写的话，那你就要去送它的 color 的 address， 这样子。那 write data 就是 write data 嘛。那好 ，OK。那它的第一轮操作就是你必须要先打开一个 raw， 你才能对这个 raw 去做存取。所以我们首先需要先送这个 ATB 的ATB 的 command， 然后之后我们才可以做读写。然后最后如果你没有用这个 raw， 你就要把这个 raw 关掉，这样子。然后这里就是你开关一个 raw 或是你读取 data， 你一定会有一个latency 的 delay。所以当你送完activate 的时候，你要等它2个 cycle 让这个 raw 打开，然后你然后raw 打开之后，你就可以送你的read 的 command 或是 write 的 command。但是这个 read 的 command 你需要等3个 cycle 以后，你才会拿到 daily 的 data。那 pretry 就是当你想要继续对这个 bank 的另外一个 raw 读写的时候，你就需要把我们现在开启的这个 raw pre-charge。所以然后 pre-charge 的话，你就需要等3个 cycle 之后才能再重新送 activate。OK， 然后这个最后面这个 raw active time 就是说就是你打开一个 raw， 它最短一定要开5个 cycle， 就是你要 你 activate 之后，你要5个 cycle，你才能再送一个 precharge 的 command 这样子。好，然后这也是刚刚跟你们讲过的一个 example。然后你可以因为我们不可能一直在比如说我们在读这个 bank 0的时候，我们可能要去等它的RCD 或是CL。那这时候我们是不是可以先去做 bank 1的指令？我们不一定要去等它这个2+3的 latency。我们可以就是我现在读这个 bank 0，但我还没有读到它的值，但我先去对这个 bank 1下 activate 的指令，这个就是 interleaving，大家可以增加你的输出跟提高你的 performance。然后这些就是一个 I/O。那read write 它都你的 output 就是像 read 你就需要读出256个东西嘛，所以你就会有256个 cycle。那write 跟 source 的话，你拉高一个 cycle，你不需要 output data，对，你不需要 output data。然后助教的 DRAM，助教就会去 Python 就会去检查你的 DRAM，跟我的 golden DRAM 是不是正确。然后 calculate 就是你需要把那4个 tree 的 output 都output 出来。那 spec 的部分就是你的就是你每一个 operation 最多不能超过1万个 cycle，然后跟你的面积不能超过这是多少？750万个 μm 平方。然后你的合成时间不能超过1个小时，然后跟你的 clock period 最多是40N 这样子。然后因为这个 lab 主要是写 pattern 嘛，那你这里有一些 spec， 像是我们刚刚讲到的，你的执行时间不能超过1万个 cycle， 或是你的 out data 必须要是对的，当你的奥贝利拉起来的时候必须要是对的，这些 spec 如果违反的话，你就不需要在 terminal 上面print 出这样子的字眼。然后助教在 pattern 里面都有给你这样子的那个叫什么我没有给他们，就是会有给你们这个 command， 就是你们可以直接复制贴上就好，就以避免说你们的名字跟助教不一样，然后导致没有判读到。然后如果有不一样的这个 spec 同时违反的话，那你就照这个输出顺序，但是你不能同时输出2个或是以上个 spec 的 error。好，然后就是你的 harvest 跟 DRAM control 都要对的话，你才有这个 functionality 的分数。那performance 2day 的 performance 不会跟1day 的 performance 一起做计算。那当你写完你的 pattern 之后，你可以用07 check pattern 去检查一下看你的 pattern 是不是全部都通过这个助教的 pattern。那你可以在你的01 run VCS RTL 这个后面加上 correct，就会去验证你的pattern 正确性。然后如果你加 spec man one 的话，它就会去检查这个 spec one，或是加 spec a 叉 one 之类的。那这不是。然后注意它，因为我们这是很那个底下有两个主要的 module，那在合成的时候，你就必须要在这个 script 的后面加上 harvester 或是 DRAM control 来告诉这个 compiler 说你要合成的是哪一个 module 这样子。OK， 好，然后就是 input 跟 AXI 的 waveform， 对，现在差不多是这样。
Okay, so this all. Have any question? If you don't have any question, we will finish this lecture. And remember, we hold the second code review session today. It's at 4:30 p.m. So if you have any question about coding style, you can come here. Okay. Correct. Bye bye.